Good morning, everyone. My name is Axel Yarahuaman. I'm a PhD student at the Structural Engineering Department at UCSD. Today, I'm going to present the project called Seismic Response of Rail Embankments, also co-authored by Dr. John McCartney. And this project focuses on the San Francisco Bay Area rail infrastructure, which is in a highly seismic region, with therefore earthquakes represent a critical hazard for the safety of the users. What happens during earthquake is the rails of the track are going to settle differentially, generating what we call a cross-layer variation, which is technically just the differential settlements between rails. This change of cross-layer variation can generate the disruption of the operation of the trail of the rail. And therefore, our research project at UCSD is focusing on characterizing the relationship between cross-layer variation and different characteristics of earthquake motions. Particularly, this presentation focuses on the details of the plane strain check table experiment on a full-scale rail embankment section as part of this larger project. How did we approach this project? We consider a half embankment specimen, considering 3 soil layers, a subgrade, a subballast, and a ballast, where the rails were monitored by linear potentiometers and also 1D accelerometers. As you can see, the conceptual designs on the left and on the actual specimens on the right. The result was that the specimen was excited until the Loma Prieta earthquake motion recorded by Corralitos station scaled to 125%. It shows that the specimen has a fundamental period very close to the fundamental period of the motion, which we believe that represents that is almost a resonance. So here we can see the settlement of the rail 1, which is positive, the settlement of the rail 2, which is positive, and also the cross-layer variation at the end that was 0.66 millimeters, which is only 3.5% of what BART states. Therefore, we can conclude that even after large earthquake motions with a period close to the fundamental period of the rail embankment, a relatively small cross-layer variation was observed. Therefore, we can conclude that the rail embankment itself is resilient to earthquake shaking due to the confining effect of the rail system. For future project, ongoing research right now it is involving additional testing to develop relationship between the different characteristics of earthquake motions and cross-layer variation for bilateral struck rail embankments. Thank you so much for your time.